too, and refresh your memories about the alkyne hydration reaction. Remember that you add water to an alkyne, it takes place with acid and mercury plus 2 catalysis, and you end up initially by adding, this is the red water that we added, you end up with an enol. It adds according to Markovnikov's rule, and then the enol through a series of proton transfers gives rise to the ketone. So this kind of chemistry is now going to be important for our discussion in chapter 19. The other point I want to make is I've redrawn the enol down here, and I've shown the electron pairs on the oxygen atom. Now, another point that's going to come to the fore in this chapter is the reaction of enols with electrophiles. Okay, so if I have an electrophile like that, then the enol can do this kind of chemistry to give you a compound that looks very much like a ketone. In fact, it is. And where you have now formed this bond, that one right there, to the electrophile, okay? So that kind of chemistry is also something we're going to be seeing a lot of. It all kind of follows from that initial discussion that we had way back when we talked about hydration reactions of alkynes. So to sum up, go back, take a look at the hydration chemistry that we talked about. Please work through the mechanism. I know it's a number of steps, but they all should make sense to you and refresh your memories. Now, where we left off on Friday was the discussion of nomenclature of aldehydes and ketones. We said that the suffix for an aldehyde was al, and for a ketone it was one. So this would be 3-pentanone. In the case of ketone, you have to tell me which carbon atom is the carbonyl carbon, because there's another pentanone, it's called 2-pentanone, and that has the carbonyl group. For pentanal, because you have a hydrogen there, there's no ambiguity, so I don't need to call this 1-pentanal. It's pentanal because there is no other one, right? Okay, so now let's take a look at the physical properties of aldehydes and ketones. And, you know, there should be no big surprises here. If you compare isobutylene or 2-methylpropene with acetone. So the only difference is you have got a carbon there and an oxygen atom. Molecular weight almost the same, but huge difference in boiling points, right? Because 2-methylpropene boils at around 7 degrees below 0C, and this boils around, a little under 60. And the reason is to be seen here. The dipole moment is really very, very different. Now remember when we talked about boiling points and melting points, we said that if you have polar molecules, then those dipoles can line up plus to minus. The Coulombic attractions stabilize the liquid or the solid, and so you have then a higher melting point or a higher boiling point than you would have expected absent those electrostatic attractions. Well, here it is. Here you have a dipole moment that's quite high, there it's quite low, so this boils higher. So then you go here to the isopropanol, almost the same molecular weight, and it still has a higher dipole moment than this, but a lower dipole moment than the ketone. And here, the boiling point's even higher. Why is that? Well, by now you know, because here you have hydrogen bonding, that the alcohols are hydrogen bonded, and that hydrogen bonding exerts a force that stabilizes the liquid or the solid, in this case the liquid. And so, if you have hydrogen bonding, that's going to result in a higher boiling point. And then if you go to the aldehyde, roughly the same, well, it's almost exactly the same dipole moment. Here the boiling point is a little bit lower, but of course the molecular weight is lower too. So, so that kind of covers boiling points. I mean, nothing I've said should be particularly shocking. The other point that we always look at is water solubility. And what confers water solubility on molecules, as I keep saying, is the ability to hydrogen bond. And so if you have hydroxy groups, you have OH groups, NH groups, or NH2 groups, or whatever, then you can stabilize the compound in the liquid phase, and it's stabilized in the aqueous phase. It will dissolve in water. So acetone does a pretty good, is miscible in water, which means you can dissolve acetone in any proportion in water because it forms nice hydrogen bonds, and critically, because the hydrocarbon piece is kind of small. Now, as these hydrocarbon pieces get bigger and bigger and bigger, then the molecule, the ketone, looks less and less like a ketone that can hydrogen bond, and more like grease, like an oily molecule, like a hydrocarbon. And so the water solubility is going to go down as these become bigger and bigger alkyl groups. Now, 2-butanone also is miscible in water, if memory serves. Methyl-isobutyl ketone I don't think is. And so this will dissolve in water, but it's not miscible in all proportions. These two are actually, these three are very common industrial solvents. So methyl-ethyl ketone, MIBK. So the other issue that we always look at is spectroscopy. Now that we know something about spectroscopy, we always talk about how these new functional groups appear. You kind of know already because when we talk about IR, we talked about carbonyl absorption in the context of double bonds, of pi bonds. And we said that the carbonyl absorption is typically the strongest peak in the IR and the one that you just can't miss. It also is the one that you look for, right? So if you suspect that you have a ketone or an aldehyde or an ester or carboxylic acid, first thing you look for, infrared spectrum, look for the carbonyl. So this is usually the strongest peak because why? Well, because stretching it involves a large change in dipole moment because carbon and oxygen have different electronegativities. And so for ketones, usually you see this around 1710. Aldehydes a little bit stiffer, just a little bit. And critically for the aldehydes, there's this unique CH stretch, it's, around here, 27, whatever. Now, so if all you have is the IR, you can tell whether it's a ketone or an aldehyde just looking for this CH stretch. But in practice, it's not really, you're never going to really look for that CH stretch in practice. It's much easier to look for that in the proton and NMR spectrum because that peak appears around 10 ppm where nothing else appears. And so when you have an aldehyde, as long as you have an NMR, you're going to tell that it's an aldehyde by looking at the NMR. You look at the IR for carbonyl, but typically you don't need that CH stretch. So this is kind of icing on the cake. You don't really need that. Now, IR is a really powerful tool because, and by the way, in the lab, you guys have access to a super nice IR machine. It's a FTIR. I can tell you that you can get all this information that we're talking about here from an IR machine that's about 3 generations back in terms of technology. Okay, so you guys have, that machine you have is really overkill. I have to tell you. It's great to have. I'm not saying it's bad, but the point is you don't need anything that good to see something like this. So even with the non-FT machines that we had really 30 years ago, you could tell the difference between these carbonyl stretches. Now, look at what you can do here. If you have a cyclic ketone, you'll notice a trend. So I go from 6 to 5 to 4 to 3 to no ring at all. And the carbonyl stretch gets stronger and stronger and stronger and stronger. By stronger, I mean the bond becomes stronger, so the frequency goes up and up and up. Remember that reciprocal centimeters, that's a frequency. And so what this is telling you is that the bond becomes stiffer and stiffer and stiffer. Once you get to ketene, it's all the way into the acetylene region. And there's a reason for this. I'm not going to go through it. This is explained in 2 ways. Your solutions manual, I believe, has a somewhat detailed discussion. But the point, the take home is that you can tell what the ring size is just by looking at the IR stretch. And that gives you an idea of how useful that is. Now, take it the other direction, where you have a conjugated carbonyl, where you have a carbon-oxygen double bond that is now conjugated to another pi bond. And so conjugation can be either to a CC double bond, triple bond, or a phenyl ring. That has a predictable effect of lowering the frequency of the stretch. And so here you can see, if it's not conjugated, this is a normal ketone frequency, 1710, 1715. If it's conjugated, it goes down to below 1700. This is not conjugated, it's about 1642. If it's conjugated, this double bond is now lower. So conjugation lowers the frequency of both pi bonds, right? It makes it easier to stretch both the CC double bond and stretch the CO double bond. Now, why should that be? Well, if you draw the resonance structures, you can see why that should be, because you have these two resonance structures where there's no carbonyl group here and where there's no double bond there, no double bond there. So in this resonance conjugate, you have single bond character for both the C double bond C and for the C double bond O. And so, to the extent that that resonance structure contributes to the reality of that alpha beta unsaturated ketone, this can be easily understood. So, bottom line, conjugation will manifest itself as a lower frequency for CO and for CC bond stretch. So the IR gives you a lot of information. It tells you that the carbonyl is there, to be sure, but look at what else it does. It tells you what kind of carbonyl you have. When we talk about carboxylic acids and esters, we'll see that you can distinguish between, and amides, that you can distinguish between ketone, aldehyde, amide, ester, and whatnot, just by IR, okay? And so by IR of the C double bond O. Proton NMR spectroscopy, we've talked about some of this stuff. 2.2 or 2.1 is where you find these, the alpha methyl, and then for the alpha methylene is shifted a little bit further downfield. As I indicated, the aldehyde is hard to miss. That's between 9 and 10 always. Not too many other signals show up in that region. And so when you see a singlet at that site, or sometimes if you see some coupling, but coupling can be weak, then you know that you have an aldehyde. I mean, there's just no, can't miss it. So NMR, proton NMR is completely diagnostic for aldehydes. C13. The carbonyl is a weak peak typically, right? Because remember the C13, the intensity of the peak, the carbon peak, depends on how many hydrogens you have. If you've got a lot of hydrogens, you get a strong peak. If you have few, you don't. Well, for the carbonyl, you have no hydrogens. And so the carbonyl peak is usually one of the weakest peaks in the spectrum. And it's usually around 200, but it's bracketed by about 190 to 210 to 220. And so again, it appears far off to the left, if you will, of the C13 spectrum, in an area where not too many other things will absorb. And so the carbonyl, you can usually see that in the C13 quite easily. The chemical shifts of the alpha carbon is not particularly helpful. We don't use UV spectroscopy very much. There's, I think, a problem at the back of the chapter that asks you a couple of questions. I'll go through this just in a cursory way. So typically for ketones and for aldehydes, you have two peaks. You have one which is called an N to pi star. And what does that mean? Well, the N means the non-bonding electron pairs are absorb energy. So the molecule absorbs energy, and the non-bonding electron pair, one electron out of here, goes into a pi star, into the anti-bonding orbital of the carbonyl. So it goes from non-bonding pi electrons goes from pi to pi star. Now, these two peaks are, this is a weak peak, that's a strong peak. And the reason this is weak, this is called a forbidden transition. Now, what does that mean? What it means is when you hear about forbidden or allowed, and we're going to see this in a slightly different context in the last chapter of the semester. What that means is that a forbidden transition is unlikely. Okay, it doesn't mean that it's completely forbidden. It means that it's much less likely than the alternatives. And it is less likely in this case, and I don't want to put a fine point on this, because of the symmetry properties of the orbitals. Okay, and so, but for acetone, it really doesn't matter. Why? Well, this is within range, but it's a weak peak. This epsilon, remember, gives you the intensity of the peak. The pi to pi star is around 150 nanometers. Remember that we look from 200 to 400. So anything that's lower than 200 is too it's too energetic. So we don't see these pi to pi stars for acetone. Now, once you get to an alpha beta unsaturated ketone, look what happens. The pi to pi star transition, which was 150, now goes to 232. If I put another double bond in there, then this is going to go even longer wavelength. If I put a third, fourth, fifth, sixth, then eventually the compound's going to be colored because it's going to absorb into the visible range. And so the end of pi star now is a little bit more probable. The pi to pi star, look at the epsilon. Here the epsilon is really is a big number. Look at the difference here. Not particularly strong peak, strong peak. So the pi to pi star transition is the one that you usually look for in the UV. In the UV, we're going to be looking, the only ketones you're going to see by UV spectroscopy are going to be alpha beta unsaturated ones or aromatic ones. Now, mass spec is really important here because it turns out that ketones are really easy to see by mass spec. You sometimes don't see the molecular ion in electron impact mass spec. Okay, so EIMS sometimes doesn't give you a molecular ion because the fragmentation is just too easy. And I've kind of shown both ways that this can fragment. It fragments either to the left or to the right. If it goes to the left, then you end up with, this is a cation and that is the neutral piece. Or it can go, again, from the left side, it can go to an acylium cation, and I can do the same thing on both sides. And so you end up with these very characteristic fragments for the ketones that you can then use to determine parts of the structure. Remember that when you ionize this, the electron that's being ripped away from the molecule is the one that's easiest to rip away, which is one of the non-bonding electrons. And so as this enters the electron beam, there's only one electron here, so I'm missing an electron. This is the molecular ion. This is a radical cation. It's a radical because I have one electron here, because I've lost an electron with its negative charge. It's a cation, and then I can do these radical reactions to get the fragmentation. So work out the curved arrow mechanisms to go from here to these two, and convince yourselves that it works on the other side too. Now there's one characteristic reaction in the mass spec that leads to a rearrangement that again can be used to identify, using mass spec to identify ketones. That's called McLafferty rearrangement, after Fred McLafferty, who taught at MIT for many years. So the molecular ion is the same kind that you get before. You pull away one of the non-bonding electron pairs and make a radical cation, and then think of it just as a radical reaction. This radical pulls off a hydrogen atom. So it goes through a 6-membered ring transition state. If I count atoms, 1, 2, 3, 4, 5, 6, You can see a 6-membered ring transition state where I have a partially formed bond there. So again, counting atoms. If I count oxygen as 1, there's 1, 2, 3, 4, 5, hydrogen 6. And so they're close enough together that I can get this reaction. Now I have a radical here. This radical can decompose to give me isobutylene and this radical cation. And that McLafferty rearrangement's really quite easy. Okay, so if it can do a McLafferty, it will do a McLafferty rearrangement. And so you end up being able to see this kind of fragment in the mass spec. Of course, you need to have that hydrogen atom that's oriented so that the McLafferty rearrangement can take place. Okay, so that kind of wraps it up for spectroscopy. The carbonyl is unmistakable in the IR. The aldehyde proton is unmistakable in the proton NMR. The carbonyl carbon atom is unmistakable in the C13. It's a weak peak, it's around 200 ppm. And then in the UV, we're not going to see the UV very much, but alpha beta unsaturated ketones, aldehydes, esters, whatever, they will absorb. And you'll see typically a double humped peak, one for the pi to pi star, strong, and one for the n to pi star, either invisible or weak. And you can tell that you have a ketone sometimes that way too. Now, to segue to synthesis of aldehydes and ketones, we've seen a bunch of ways to make these, right? And so it always helps to review the methods that you know for synthesis of a particular functional group, in this case ketones and aldehydes. So one of the ways that we know to make these are from alcohols by oxidation. So I can take a secondary alcohol and oxidize it to a ketone. I can have a primary alcohol and I can oxidize it to an aldehyde. And then you can figure out, well, how did I make this, how do I make alcohols? Well, primary alcohols like this, you make by hydroboration oxidation. And so you should remind yourself of how that works. Secondary alcohols like this, yes, I could make that by hydroboration, oxidation, and cyclohexene. But that one I could also make by hydration of cyclohexene. Or I could make it by oxymerturation, demerturation of cyclohexene, and so on. So this would be one way to make a ketone or an aldehyde. Another way is from a Friedel-Crafts. I mean, we just saw that not so long ago. The third way was the way I talked about this morning, and I said, please go and look at the mechanism. That's the acid and mercury catalyzed hydration of an alkyne. And finally, a hydroboration oxidation to get to the alcohol, which then gives you the ketone, and or a hydroboration oxidation to give you directly the aldehyde from the alkyne. So these are all ways that we know to make carbonyl compounds, to synthesize carbonyl compounds from other starting materials. Finally, don't overlook ozonolysis. That's kind of a specialized way of making carbonyls, but we know that we can chop in half CC double bonds using ozone. Remember that if I start with methyl cyclohexene and I treat this with ozone, I get an adduct, and that adduct rearranges and so on. And then what happens eventually is that I end up with a carbonyl here, and there's a hydrogen there, and a carbonyl there. So that would be the ozonolysis of a cyclic alkene. Now, nobody said that the alkene had to be cyclic. And so if I do ozonolysis of something like this, then I'll break the bond as shown. From one piece I'll have acetone, that's from the top piece. From the bottom piece I'll have the cyclohexane carboxaldehyde, that's that. Okay, so we've seen ozonolysis before. It's a good idea, if you've forgotten what it is, to go review. And then sodium peroxide is also a way to cleave vicinal diols. So if you have a dihydroxy compound with two hydroxy groups on adjacent carbon atoms, then you can cleave that using sodium peroxide. And if you've forgotten that mechanism, it would be a good idea for you to go to take a look at it. Okay, now this is all introduction, and really the heart of this is going to be reactivity of ketones and aldehydes. And so let's take a look here. So we're going to see this again and again and again, and hopefully it becomes second nature. But there are two kinds of reactions that we're going to see. And the first one is nucleophilic addition to the carbonyl. So if I have nucleophiles, we'll see lots of examples of different nucleophiles, and these can form a bond to the carbonyl carbon atom and generate this tertiary alkoxide. Okay? And that tertiary alkoxide can be protonated in the workup, and I end up with a tertiary alcohol. And if it's an aldehyde and this is a hydrogen, then it's a secondary alcohol and so on. So that's one kind of reaction. Okay, so we take advantage of the electrophilicity of the carbonyl carbon. The second type of reaction takes place at the relative acidity of the alpha protons. So these, as we'll see, these protons are quite acidic. They can be removed by base to form an enolate. Not an enol, but an enolate, right? I showed you this just this morning. I showed you that reaction of an enol, right? I showed you this enol reacting with an electrophile, electron pair. Well, it follows that if I pull that proton off and put a negative charge on the oxygen, then this species is going to be an even better nucleophile than the enol. It's charged, if it's an enolate, it's a better nucleophile than the enol because, other things being equal, charged nucleophiles are more reactive than uncharged ones. And so here's the charged nucleophile, an enolate, that ATP tells you it's got a negative charge. It's a strong nucleophile that reacts with electrophiles and forms bonds to the alpha carbon atom. And so what emerges from this is a picture of reactivity. It's got to kind of have two parts to it. So whenever you have a carbonyl compound, any carbonyl compound as it turns out, so I don't care what's here, I don't care what's there, and I have at least one hydrogen atom there, okay? Then what it means is that this can do two things. I can either add a nucleophile to the central carbon atom and end up with an alcohol, or I can pull that proton off with a base to form an enolate, like so, and then the enolate can react with an electrophile, like so, to form a alpha alkylated ketone. So it means that both carbon atoms, both this one and that one, both of these carbon atoms are reactive. They're reactive in different ways, but I can do reactions at either one I want. So I can either perform reactions at the carbonyl carbon, or I can perform reactions at the alpha carbon. Okay, so keep that straight in your mind so you don't get confused. So the first reactions we're going to talk about are these. And so let's start with the very simplest one we can think of, right? The simplest reaction almost always, is reaction with a proton. I mean, what could be simpler, right? So, you know, acid-base reaction with a proton. Well, nothing new here. We have electron pairs on the oxygen atom, and if I allow this to react with any kind of acid, so this can be either a Lewis acid, or it can be a metal cation, i.e. a metal cation, it can be an uncharged Lewis acid like BF3, or it can be a proton, then I'm going to get an acid-base reaction. Nothing new here. It's just electron pairs doing what they always do. And the other reaction is nucleophilic addition. That's this reaction here. Nucleophile adding to the carbonyl. And I'm going to show it a little bit differently with the nucleophile bonded to whatever the counter-ion is. Then you end up doing an addition across the CO double bond. So that's the other kind of reaction we're going to see in this chapter. Another reaction that we need to remind ourselves, we've seen this in Chem 272, and that is the oxidation of an aldehyde to a carboxylic acid. recall when we talked about redox chemistry, we talked about chromium plus 6 being used to oxidize alcohols, secondary alcohols to ketones, primary alcohols to aldehydes, except if the primary alcohol to aldehyde oxidation was done in the presence of water, it didn't stop at the aldehyde, it went all the way to the carboxylic acid. And so here when we say oxidant, think water present too. Okay, and we're going to remind ourselves of why water is important for this kind of oxidation. Okay. So, we just saw that aldehydes and ketones are Lewis bases, right? I mean, they have electron pairs on oxygen, so yeah, they react with acids. You know, nothing surprising. And one of the acids they react with is hydronium ion. What you notice, however, is that the equilibrium strongly favors ketone and not the protonated ketone. Why? Well, because the pKa of hydronium ion is only about minus 0.2.5, whereas the pKa of this stuff is minus 6 to minus 7. So the difference, if it's minus 6, there is a 3.5 log unit difference. So you're only going to get a few parts per thousand of this in this equilibrium. Now it turns out that few parts per thousand is enough to catalyze a lot of reactions and to explain a lot of stuff, but remember that the equilibrium typically will favor the ketone. Okay, now, look at this cation, and, or this one, and it's not resonance stabilized. Look at this cation, and it is resonance stabilized. And so now the question is, well, gee, how come the more stable, you know, the resonance stabilized cation isn't favored? And that kind of makes no sense, right? Because you would think that the resonance stabilized one should be, you know, that should be a weaker acid, not a stronger acid. And the heat comes from the vapor phase. If you look at the vapor phase, then it is. And so this is another really good example of something that I've said again and again, and that is that, you know, when we look at these reactions, we kind of ignore something that's very, very important often. That's the effect of solvent. And so these reactions, when we discuss them, you know, there's an abstraction on the board, on paper, on the book. These reactions are kind of shown as taking place, you know, not in a solvent. You have to remind yourself that it's in a solvent. And this is a good example of why. Because the solvent here is doing a big job for us. And what it is doing is, whether it's this cation or hydronium, it gets stabilized by hydrogen bonding. So don't forget that these hydrogen bonds donate electron density. So the oxygen here has a delta plus, and it's donating electron density, the delta minus here, which then stabilizes this cation. So in solution, which is where we live, or where we do most of our chemistry, in solution, this cation gets stabilized, and that's why this has a pKa of minus 2.5. This cannot be stabilized through hydrogen bonding, and so that's why it is a much stronger acid. So if you don't think about what's going on with the solvent, then you don't really, then this doesn't really make sense. No? Okay. So, so acids react with carbonyl compounds because of the non-bonding electron pairs. No surprise. Now, the first real reaction we're going to look at is cyanohydrin addition. Now, cyanohydrin formation. So this seems a bit strange, doesn't it? I mean, you know, cyanide is poisonous, and you know, you think, well, you know, how important is this after all? I mean, is this really an important reaction? Adding hydrogen cyanide to acetone to form acetone cyanohydrin? It turns out, yeah, this is really important, and it's done on a huge scale. And it's done on a huge scale industrially because acetone cyanohydrin, believe it or not, is the starting material for a very important plastic. And so, so this stuff here, acetone cyanohydrin, gets converted through a series of steps to methyl methacrylate. Okay, this stuff. And you can kind of see where the carbons are. These three carbons are these three. This, oops. So these three carbons are these three. And the nitrile, it turned into this ester group here. So the branch point here is there. And so we're going to learn how this all happens. But it turns out that this is used for plexiglass. And so plexiglass starts its life as acetone and cyanide. Okay, so it turns out cyanohydrin, in addition to aldehydes and ketones, is also used for making acids and amino acids, but that's another story. So, yep, hydrogen cyanide, a fairly weak acid, which means this is a fairly strong base, and it's a good nucleophile. So hydrogen cyanide, you'll notice it's not like HBr, where you have a pKa of -8 or whatever, -7. And so here you have a very good nucleophile that adds the carbonyl, generating a negative charge, and then water provides a proton, and you get an equilibrium of acetone cyanohydrin. Now this reaction works, and it works quantitatively, which means that the acetone and cyanide, equilibrium all goes to acetone cyanohydrin. On the other hand, if I try to do the same reaction, not with a compound that has a carbon-oxygen double bond, if I try to do it with a compound that has a carbon-carbon double bond, then this doesn't go at all. This doesn't work. You can let cyanide sit around with ethylene until hell freezes over, and nothing's going to happen. And the reason it doesn't happen, I think you can see, that the transition state leading to this compound is stabilized because there's negative charge developing on an electronegative oxygen atom. The transition state going from here that would lead to this compound, which doesn't happen, would have a negative charge developing on a carbon atom. This would be a very, very strong base with a, the conjugate acid with a pK of over 50. And so, of course, this doesn't happen, and that does. And so the fact that you have this polarized carbon-oxygen bond means that you are able to get this kind of nucleophilic addition. Now, this happens, notice, even though the carbon-oxygen double bond is about 15 kcals per mole more stable than this bond. And the reason is what I said, is that it's the high basicity of the carbanion that would have to form. So if you're going to do an addition to a CC double bond, you're going to form a carbanion. If that carbanion is very strongly basic, forget it, it's not going to happen. And so the polarization of the carbon-oxygen double bond is what you need for this to take place. And this is going to be true not just for cyanide, but for each and every nucleophilic addition that we talked about. And nucleophilic additions, not just to ketones, not just to aldehydes, but to esters and amides. Okay, so now you take a look at this. Say, well, how does this take place? First of all, it has to be conserved. Well, it has to be conserved. The bond forming process represented by this arrow, and the bond breaking process represented by this other arrow, those have to be taking place simultaneously. Why is that? So I've shown, so these two arrows, remember the arrows originate in electron pairs. So this arrow shows the formation of this red bond, and this arrow shows the electron pair now sitting on oxygen. So I start out with 2 electron pairs and I have 3. I said that these two processes have to be taking place at the same time. Why? I didn't hear a single answer. I heard some noise, but I couldn't make out what you said. Louder. Yeah.
You would have too many bonds with the
Yeah. Okay. So the bottom line is that if you do it the wrong, if you do it one bond at a time, you're going to end up with an octet rule violation where I'm pointing. So you can't have that. Okay. Well, that's fine. So that doesn't tell us anything, though. I mean, well, it tells us something, but it doesn't tell us exactly how this process takes place. So so the octet violation tells you that you will end up, as you pointed out, with too many bonds to that carbon atom. So then that begs the question, fine, I take that electron pair from cyanide, I push it into the, I form the cyanide carbonyl bond. Where does that electron pair go so that it doesn't violate the octet rule? And the answer is that it has to initially occupy a pi star orbital, which is empty. So electrons exist in orbitals, right? And the only orbital that it's going to see that has room in it is going to be the pi star. So here's what happens. This electron pair, so the cyanide approaches this carbonyl along a vector that is roughly 120 degrees, okay? And it does that because along that vector, you get the best electronic overlap. It means that the electrons that are in this orbital overlap best with the empty, this is the pi star empty orbital, and notice that the polarity changes, so it's an anti-bonding orbital, it's empty, but this is where the electron pair goes. So as the electron pair enters that pi star bond, I start to break the pi bond, and as that happens, then this bond goes from a double bond to a single bond, and as that happens, you go from sp2 to sp3 hybrids, and as that happens, you go from 120 degrees to roughly 109.5 degrees. So what you have to visualize is the cyanide approaches the carbonyl according to that vector, and as it approaches, the carbonyl starts to change. It starts to going from flat to tetrahedral. And at the end of the reaction, then you have a tetrahedral carbon atom here with a fully formed bond. And so as the reaction progresses, bond angles change to about 109.5. Now, the angle of attack, notice I kind of indicated it's this way. It's not coming in that way. And the reason is because you get better orbital overlap in this angle. So this is going to be the case whether or not the nucleophile is cyanide or anything else. So any nucleophile is going to approach that carbonyl according to the same trajectory. Okay, so that trajectory has been calculated, and the angles are pretty much, what I've indicated. The electron pair from the nucleophile is going to initially occupy the pi star, the empty pi star, which is the lowest unoccupied, lowest in energy, unoccupied molecular orbital for the carbonyl. So now, this was cyanide addition, and so let's go back and just kind of take a look at how this happens, just to refresh our memory. So cyanide acts as a nucleophile. It reacts with the partially positively charged carbonyl carbon. That happens simultaneous with cleavage of the CO double bond and formation of a negative charge there. Proton transfer completes the process, and you end up with the cyanohydrin. Okay. So that's how you form a cyanohydrin. So, okay, so what other nucleophiles do we want to look at? Well, one that is not maybe the most exciting one is water. So water adds to carbonyls as well. And you can form carbonyl hydrates. What's a hydrate? It's exactly what it sounds like. It's the carbonyl plus water. So if I start out with acetone, then this would be acetone hydrate. This molecule is composed of one molecule of acetone and one molecule of water. And the mechanism that I've shown is acid catalyzed. So the first thing that happens in acid is that you end up activating the carbonyl by proton transfer from the acid to the carbonyl. That gives you this species. This is what? This is the conjugate acid of acetone. Now, I can think of that conjugate acid of acetone, and I need to remind myself that this species, that has a resonance structure that looks like that. Okay, so in this resonance structure, this is a cation, and this carbon atom has a full positive charge. And so, unlike the resonance structure that I can draw here, which is dipolar, this is a cation. It's a carbocation. And so water reacts the way it would with a carbocation to give you this alcohol, the diol, and then loss of a proton reveals the hydrate. Okay, so what did I tell you last time about mechanisms? Remember? Yeah, you got to reproduce these on a piece of paper when you go home. Okay? So don't rely on your memory or on memory either of the lecture or of the notes. Make sure that you can reproduce this step by step correctly. Okay? It's not hard, but it should become muscle memory. Okay, so let's go through it again. In acid, this is going to transfer a proton. That activates the carbonyl, the nucleophilic attack. That gives you a tetrahedral intermediate. This is the tetrahedral intermediate. So at this step, I've gone from sp2 to sp3. I've gone from planar to tetrahedral, and then proton transfer completes the process. Now, the other thing I want you to notice is that this mechanism and the preceding one with the cyanohydrin are quite similar, because you end up adding a nucleophile carbonyl, going from planar to tetrahedral, and then in the last step, there's a proton transfer. Okay, it's not quite the same, but they all share that sequence of events. Now, in the case of acetone, and unlike what we saw for cyanohydrin, the equilibrium overwhelmingly favors the ketone. So if I just take acid and water and acetone, I get a few tenths, maybe a few hundredths of % of that stuff. I don't get very much of it. And so with aldehydes, on the other hand, that equilibrium very often favors the aldehyde. And there's one particular aldehyde where the hydrate is actually favored, and that's trichloroacetaldehyde. This goes by the trivial name of chloral, okay? And so when you buy chloral, you don't buy chloral. What you buy, if you can buy it, and I'll explain what that means. You end up with this stuff, which is called what? Chloral hydrate. And there's no equilibrium for that. It's all chloral hydrate, 100%. And so what's chloral hydrate used for? Anybody? No. This predates roofies, okay? So this is what you put in somebody's knockout drops, right? So if you put this in someone's drink, they pass out.
Hey, what are you teaching us?
And what I teach you is devoid of any kind of moral content. You supply the moral content, and all science is like that. So if you read the paper this morning, you would find out that in New York, they have a policy now where people can be convicted on the basis of DNA evidence that is really extremely shaky. So they take, use polymerase chain reaction to amplify DNA. Works really well if you've got a lot of DNA. If you have just a tiny bit of DNA, it doesn't work very well. Why is that? Well, because contamination is easy to happen. And yet people are being convicted based on really lousy science because it helps the prosecutors. Now, you should learn about polymerase chain reaction, but then you should have the ability to make a moral judgment about, where is a good application and where is not. Anyway, we'll pick up our discussion.